Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, we would like to tell you all that in this session today we would be talking on centrality and complex graphs, and for this very discussion we have once again with us in our studios Dr. Aditya Sinha. Dr. Aditya Sinha is currently teaching in one of the leading institutions, and she has immense experience. We hope that her experience would definitely help us out in understanding the topic centrality and complex graphs. Hello ma'am, welcome to the DSEC lecture.
Hello everyone. In this lecture we are going to study on the centrality aspect. Last lectures we talked about what type of graphs can be there that model the real-time networks. Okay, so in this lecture we are going to cover which nodes or which vertices in a given network model are considered more important than the others. Right. So, we will try to find out different mechanisms that are there for computing relative importance of the nodes in the network, and also we will come across some complex graphs like hypergraphs that extend the connectivity of nodes from two nodes to even more nodes that can be connected with the help of a single edge. Okay. Then we will also come across multi-graphs and random graphs, etc. So, to start with, we will visit different centrality measures that include degree centrality, then closeness centrality, decay, betweenness centrality, information centrality, and of course, one more very important is cross-click centrality, also known as click centrality. Okay, so far the fundamentals that we have known, the fundamentals and the basic concepts, the basic terminologies, etc. What we are trying to do is we want to map the basic concepts, the fundamental theorems of graph theory to the real world networks. Okay, so when it comes to simplifying the network complexities, yes, graph theory helps a lot, as in it helps to determine the global patterns of the network. Now, global patterns can be the path lengths between two or more nodes in the network, what type of degree distribution it's following. Either it is a random distribution, or it might be that the distribution follows some particular mathematical formula, some mathematical distribution that are available. Okay, so when applying these APL, the average path length, geodesic, and all concepts on a particular graph, what we find out, try to find out is whether two nodes are reachable or not. If they are reachable, then what is the length of that shortest path? Okay, and even which are the nodes that can be reached very often, like they serve as hubs, and others are other than hubs, they are known as authorities. Okay, so the network distribution, what type of distribution it is. So all these global patterns, they can be revealed with the help of those simple graph fundamentals that we have already studied. What else we can conclude is the segregation pattern. These are those patterns that try to find out the similarity, and with the help of which clustering, or say for example some inherent community that is there in the large graphs can be revealed. Okay, so it can be a type of homophily over node types in the sense it can be classification. If we are talking about this social network, it can be the age of the person, the gender, the class, what type of social belief he shares or likes with the other friends in his social circles, etc. And how this network, the whole network is integrated, and what type of impact it throws, this homophily and similarity over the rest of the network. Okay. Apart from this, the local networks, the local patterns that are there in the network can be known by analyzing the different community detection methods. Okay, which communities are like closely connected or which are tightly connected, loosely connected, the communities that play a very important role in the network, etc. And this can be done by checking out what type of clicks, how many clicks are there in the network. Clicks, as we know that they are the subgraphs in which all the nodes are connected to each other. They are tightly coupled. Okay, so what type of triads are there, number of triads are there, if there is a transitivity relation is there or not. It's like if there are 3 nodes, say A, B and C, and A is connected to B and A is also connected to C. So that is A is common to both. Whether you take up computer networks into to cite an example, say a common receiver is there for 2 transmitter, then whether those 2 transmitter can be, is there any way that they can be linked to each other so as to form a triad, a click of size 3. Okay, so this type of pattern discovery things can be made out, can be concluded with the help of studying the local patterns of the network model. And what else? Of course, the position, that is the main focus of this lecture, the positioning in the network, the type of neighborhood a particular node shares, and the influence that it imparts to the rest of the network. The different centrality measures that we will be studying. So the first thing that we have to understand, what is the significance of centrality? By its name, it's very clear that central means what? It's something that is to be in the focus, or that is something which is more important than other nodes in the network, right? So it's basically, we can say that they are network based measuring parameters, and this can be used, this type of phenomena, the mechanisms, they can be used for recognizing some important nodes. These important nodes, they normally act as a focal point in say for example technological networks. Say there is workstations, there are so many base stations in every area. Okay, now if we want to find out which workstation is like more popular in the sense, maybe the workstation that is able to support maximum number of substations in the area, that workstation is known to be like yes, it's going to have a very good power resource, or maybe the connectivity, the link quality of the whatever link service it's providing is good. So this type of different measures, different quality of service measures could be there, on the basis of which we can find out that which are the focal point in any network, maybe say technological networks, etc. Secondly, yes, identifying most influential personality in a social network. When it comes to social network, social events are also important. So different types of analysis can be done just by checking out the interactivity, social interactivity graph, and we can see that if nodes are our events, then we can find out that which event is being most popularly visited or most frequently visited by people, by some business organization, or what type of people are visiting such events, or it can be the personality, some famous personality, etc. Okay, so it's all about the influence that we are talking about. The person who is having a very central position, or event who is sharing a very central position, and is also throwing some impact, some positive impact, some good influence over the society. Okay. What else? If we are concerning some business oriented networks, then our nodes would be the strategies, maybe the plans, etc. So when we are speaking about this centrality thing, then what we are trying to do is detecting the key strategies that are there in the business, that are known to be popular for past many years, or they might be acting as a benchmark, etc. Even when it comes to disease network, or say socially interacting networks, that is the physical networks in which people like we are talking with each other, we are sharing ideas, etc., or we are working together, right? So what type of connectivity is being shared by in such type of interactive networks? So in such networks, it reveals that who are the spreaders of say infectious disease, or like how to some type of anti dose can be given to those people so that it can get restricted. So this is the reason which is why whenever a person is suffering from infectious disease, the doctors ask to isolate themselves so that it does not spread to the entire network, because obviously such infectious disease, the spread of such infectious disease depends upon how frequently that person is interacting, to what type of community it is interacting, etc. Okay. Also in supply chain networks, centrality can be playing an important role as well, because in such networks the suppliers are very important. So to find out the central suppliers, the central purveyors who are supplying goods of better quality or something, right? So this is the main significance of why centrality is considered a very important issue when it comes to networked communities or network structure of nodes. Okay. And this type of measures, this type of phenomena, they are influenced by two things. The one is flow based and the other is structure based. Okay, so what are these? Flow based means that the nature of transfer is more important when we come across or when we are concerned about how the information is flowing in the network. Okay, when we are mainly concerned about how it is flowing, what type of path it is taking, or whether that path is being taken redundantly or not, likewise. Okay, so this is based on what type of information, how it is flowing in the network, which links are more important, whether those links are stable, they are reliable, etc. Okay. The second is the measure of cohesiveness. It means that we are interested over the underlying structure of the network, how the nodes and links are like they are spread apart. Okay. So on the basis of information flow and underlying structure, we have certain more subclasses. And what we come across is through these measures, we are able to discover new routes for say efficient transmission, and different measures to analyze the degree of cohesiveness, the degree, the extent to which this underlying structure is important for finding out different centrality over different sets of nodes. Now, the categories, as told, that on the basis of network flows, what is net flow actually? It is basically the network which is known as the interconnected structure of nearby nodes that are connected. So the main thing is we have routes over here, and whenever we have routes, it means that we want to pass some message or start some communication through these routes. Okay. So the flow of information is very important here, the main concern. Okay. So we are also interested in the type of path that are available to us, or it can be the number of traversals, whether a node is visited once, twice, or what is the minimum threshold that edge can be visited. It cannot be visited more number of times because it might be shared between say several other like stations, requesting stations. So we cannot dedicate a particular edge to a particular station. Okay. So say for example, there is some scenario where many stations are there, they are all sharing the same link for transferring their packets. So what is there has to be some constraint on that particular link or that particular edge, that it cannot be dedicated to a particular station for more than once or twice, etc. like that, right? So this type of path connectivity is measured by some measurements like walks. It can be trials, it can be paths, geodesics, and average geodesics. These are the terms that we have already visited, right? Walks are what? In which the nodes and links can be traversed any number of times. So there is no constraint on how many number of times the nodes, the vertices and edges are to be visited. Okay. In trials, what happens? Nodes can be visited multiple number of times, no restriction on the visiting of the node, but yes, the edges can not be traversed more than once. Okay. So this is a restriction. And what then we have paths. In paths, both nodes and edges, they cannot be traversed more than once. Geodesics are nothing but they are shortest paths. Okay. And average geodesics are what? They are the average shortest path, the average geodesic that is there in the network. As we are interested in say for example, two stations are there, we want to send, we want to communicate our packets, and we are interested to communicate in a manner that involves least amount of delay. So, in that case geodesics comes into the scene. Then on the basis of network structure. Network structure is very important and it is defined, it can be described in terms of the node distribution, how many number of nodes are there, and these nodes are in what way they are localized, etc. And then of course the link formation is important, whether the links are dense, whether all the nodes are connected, almost connected, fully connected, or sparsely connected, etc. So, the node and the link formation, they are the node distribution and link formation are going to define the network structure. So, we can have a dynamic network structure. On the basis of this, again we have some more subclasses. The first is radial, and then we have medial. In radial centralities, they normally track the connectivity and path lengths, and these are the parameters that are mainly associated with the individual nodes acting as either source or the target. Okay, so we are concerned the prime importance is that particular node and nothing else in the network. Okay, so in that case there can be some centrality measures available to us, like the degree centrality or the closeness centrality, the ranking, what type of ranking it is sharing with respect to other nodes in the network. Okay. And medial centralities, these are the ones that helps to track the relative connectivity of the entire network when going through that node. When we are passing, we are traversing a particular node. That node is not our final destination, of course, it is not our source, not our target, but what is the importance, if you want to know that what importance it shares if I want to frequently go from one place to another, and there is only one way of going, that is going through that node. So, this type of nodes, they often act as junctions. Okay, junctions in railway network, or junction in simple road networks, or even in the computer networks and wireless wired networks, that which are the main junctions base stations that are available. Okay, so this type of connectivity, this type of centrality measures are normally cross-click method or Betweenness method, and many more eigenvectors, etc. So, let us come across the centrality now. Okay, so the first one is degree centrality. Now, what degree centrality is trying to say? It says that how compact the immediate neighborhood of a node is. Okay, it can be the local neighborhood of the node can be very densely packed or sparsely packed, and accordingly we can say that the person, if we are, say for example, we are interested in a social network, then we can say that whether that particular person is very popular in its own area, within its own community or not, like that. Or if you are talking about computer network, then say in a wireless sensor network, we can say that if a sensor is communicating or it is having connections with many number of nodes, we can say that such nodes are very important, as they can communicate to maximum number of nodes in the network. So, they again can act as hub sensors. Okay. And such nodes often act as cluster heads for balancing the load within a cluster when it comes to sensor network or any wireless network. Okay. So, this is all about degree. Then what is closeness? Closeness is a parameter, it is a measuring parameter that tells about the reachability of a node. That is, if a person or say a message has to be transmitted and it is on one node on the network, say the nodes are specifying a particular source stations, etc., then what is the measurement, or what is the degree, or to what extent my message is going to reach quickly to that particular station, whichever is my target station. Okay. So the main concern over here is the reachability. To what extent a node is having the highest reachability in the network. Its positioning is very important. Positioning means that its physical position in the given network of nodes. Okay. Then of course we have decay. Decay is a very important parameter again. It is a rate at which information from indirect neighbors deteriorate. Okay. It means that as we go from the direct communicating neighbors to the indirect ones, indirect maybe by crossing 2 links or maybe crossing 3 links, so they are just going farther off from my central position. So how the information that is coming from a far off distance, obviously the relevancy is going to decrease, because the information is coming from some maybe my far off neighbor, or maybe some very far off stations that are situated far off from my position. So whatever information are coming, whatever transmission that I am receiving, maybe the reliability, which is it's an apparent fact that it's going to decrease. Decay says to what extent, to what rate this is going to decrease. Okay. Then of course we have betweenness. Betweenness is about the well positioning in the network, but it is different from closeness, because closeness also tells about the positioning in terms of reachability, but betweenness is positioning in terms of how good it acts as a bridge or gateway. Okay. Important agent without whose help a particular task cannot be achieved, say for example. Okay. And then we have information. Information centrality, it is associated not only with node but also with the network. We'll see just within few minutes that information centrality is one of the very important one, because it helps to give an insight of if a particular node that is maybe having a high closeness centrality or high degree centrality, if that particular node is removed from the network, then what impact is being happening to the rest of the network in terms of maybe the connectivity, etc. Okay. Then eigenvector, or also known as the popularity or rank, or even the influence centrality. Okay. It says what importance a node is going to share in a given community. And this importance is what? This is basically the relative ranking in the entire graph. And the wide measurements, we can see that wide centrality measures are available. So, and none of these measurements can be alone taken as a single parameter or single measuring parameter to evaluate the entire graph. Okay, so again, as the graph structure, the underlying graph structure is, or say for example, the type of information that we want to spread in the network, the flow of information, etc. On the basis of that, we have different measurements, and most often these measurements are taken into say a hybridization model in which two or more, the impact of two or more centrality measures are taken into account to have a more accurate value of importance of a particular node in a network. Thank you. Welcome viewers. So starting with the degree centrality, degree centrality captures the connectedness of the local neighborhood, okay, as we have already discussed. So let's see with the help of an example. In this example, we can see that we have a nice graph of over 15 nodes. So if say for example we want to find out the degree centrality of the third node, okay. So in this how we are going to find out, we are simply going to count the number of links of the degree, that is the degree associated with that particular node, say how many links it is sharing with its neighbors. It's 4, right? So the degree of 3 will be 4, and it is being normalized by a factor n minus 1. N is the number of nodes in the network, the maximum number of nodes. So here the maximum number of nodes is 15. So we take it as 15 minus 1. So two very important questions that arises over here, that what is the significance of this normalized version or this normalization itself. The main importance is that the degree associated with different nodes is different, all right. It won't be a distinct value, or it won't be lying within a particular scale, so as to scale down to a particular say range. Say we want to scale down the value of degree centrality between 0 and 1. So what we do, we develop a normalized version of the same, okay. This helps to say for example, if you want to just compare the degree centralities of different nodes in the network, then what we do, we can simply take the fractional values and we can just put them in ascending or descending manner, and we can find out that which node are better than others in terms of degree centrality. For that purpose, normalized version is very important, and here the normalization is being done by n minus 1, which can be a second question, that why n minus 1? It's because n, which is clearly the total number of nodes in the network, and we are subtracting one node because it is that node we are interested to find out the degree centrality of, right. So that's why it's n minus 1. So by dividing it by n minus 1, we get some value that is a fraction, and it lies between 0 and 1, strictly between 0 and 1. Okay, so D3, if you find it out in that manner, you come across the value 0.28, okay. And we can see that here node 15 is having a very dense local neighborhood, okay. So it's a very compact one. So if we want to find out the degree centrality of node 15, you can see that it's coming out to 0.42. Apparently we can see that it should have a high degree centrality, and actually also when you apply the centrality formula, you can also see that it's just more than double of 3, the node 3, that is its local neighborhood is associated, okay. So more is the degree centrality, very clearly better is the compact, better will be its neighborhood, the size of the neighborhood, the compactness of the neighborhood, okay. Now this was all about the undirected graph. Now what happens when we are taking directed graph as an instance? Here what happens, that we know that in directed case there are inflows and outflows, the arrows coming towards a particular node or the arrows that are moving out of a particular node, okay. So here the degree centrality would be a little different. It will be decay in, that is the degree of all the arrows that are coming towards itself, okay, all the summation of all the inflows divided by the same normalization parameter, and for the out degree, in degree and out degree that we have. For out degree, what we are having, all the arrows, we are summing up all the arrows, we are counting all those that are going away from the node, okay. So this is all about degree centrality, but degree centrality is going to miss certainly very important informations, because it only says that what is the size of the local neighborhood, okay, whether there is a direct hop connectivity, if there is, then with how many nodes there is a direct hop connectivity, etc. But it certainly does not say about where a particular node is positioned. Does it imply that if immediate local neighborhood, if it is very compact for a particular node, whether it is reachable also in that manner or not. So it says nothing about the reachability, nothing about the positioning in the network. So to understand more on this, the accessibility, the reachability aspect, we move on to the closeness centrality. Closeness centrality, denoted by CLI, it keeps track of the relative distances from a node I to the other nodes in the network. Okay. So again, this is one more centrality. So obviously, whatever value it is going to give, that will also will not lie between 0 and 1. So to scale it down to 0 and 1, what we do, we need a normalization parameter over here. So the normalized version will be n minus 1. N minus 1 is the normalization parameter over here, and its formula is basically 1 upon the summation of all the shortest paths. Okay, shortest paths here it's denoted by Lij. So Lij is the summation of all the shortest paths that are there between a particular node I and j. Okay, so let's see how CL15, CL3, as you can see, the values are being calculated over here, right. Now, the one important thing is why this type of normalized version is taken here, which is a little different from the degree case, right. So, this is all because we have a special case in closeness centrality. What is that case? It's if node I is connected in one hop with all other nodes, that is, we are dealing with a star network, say for example, then if we are summing out the number of shortest paths that we have, right, it will come up to 1, because what is the length of the shortest path now? It's 1, because in one hop, if we are taking example of a star network and our node I is the at the center, it is connected to all other nodes in the network with only one hop, so it's nothing but 1. So that way the centrality measurement is defined. Now let's take an example to understand the centrality. Okay, we take the same old graph over here, and say for example we want to find out the centrality of node 3. 14 is what? 14, let's go back, it's n minus 1, that is 15 nodes minus 1, 14. Okay. And what else? We have this 1 upon 4 plus 8 plus 12 plus 8. So what these are? These are basically the hops multiplied by the number of neighbors. Okay. Let's see, those number of nodes that are reachable in one hop or direct hop. Okay, so let's find out what those nodes are. You can clearly see that direct reachability from node 3 is 1, 2, 4 and 8. Apart from these nodes, there are no other node that is reachable in one hop. Okay, so the value is 1 because it's reachable in one hop, multiplied by how many such neighbors are there? 4. So we get the value 4. Similarly, for 2 hops, how many such neighbors are there? There are 3 members, 7, 5 and 15. You can just check it and verify. So it comes out to 8. Similarly, we go for 3, we go for 4 depending upon the size of the network. In this particular network, all the nodes are being covered by starting from node 3 to all other nodes in the network in 4 hops. So we are stopping in the 4th hop itself, and whatever values we are getting here, we will sum it up and we get 14 by 32. Okay. So this way the closeness centrality is being calculated. Now again, for the directed case, we will have in closeness and out closeness. Okay. In closeness is given by the first formula, and out closeness is same, it's given by the second formula. The only difference over here is of the direction. Now we are going to check out for the shortest paths on the basis of its directivity. Even if there is a link and there is a connectivity, like we cannot say that they are connected in a directed manner. So we have to check out for the direction as well. Okay, and more often the in closeness centrality is known as prestige when we come across a citation network. What is actually a citation network? It is a researchers community where researchers often publish their work in form of conferences or journal papers or some article in magazines, etc., maybe patents, etc. So and their work are, when they are being cited, when they are being referred by others, they get a prestige in the network. The maximum number of citation, the maximum number of references that that particular researcher's work has earned. So this is what the citation network shows. So in closeness, that is all the inward arrows. So how many number of inward arrows a particular person is gaining is showing the prestige of that person in the network. Okay, so in closeness is having a quite importance. So we can see over here that how in closeness is computed for node 2. As you know, it's simple, as we have done earlier for the closeness of node 3 in the other graph. It's same, it's just that now we are following the directions as well to establish connectivity. So 0.47, it is nothing but the prestige of node 1. Now, decay centrality. Decay centrality is capturing the impact of a node which is directly or indirectly connected. And now when it is indirectly connected, directly connected we understand that is it's only a one hop. Indirectly connected can be like 2, 4 or maybe even more than that. So we are interested to know that as the number of hops increase, what impact is laid on the information that it is holding, whether that information, the value of the information is going to degrade. Yes, obviously it will be degrading, but by what factor it is getting degraded. Okay. So for this we have a decay constant because it's degrading, or we can say that it's decaying. From that this name is coming up, decay centrality. So obviously we are having a decay constant delta, and it will lie between 0 and 1. Okay. So here is 3 important cases that we have here is if the delta is something that the network administrators are choosing. It's a predefined model parameter. Okay. So we can just change the value of delta and we can see the impact. It's likewise. So if you're taking some value delta that is approaching towards 1, okay, then it means that it's becoming the component size. It means that we are emphasizing on all indirect connections. That we want more and more information from far away places, from far away nodes. That is what we want. If we are setting the value delta more towards 1. If it is more towards 0, say 0 point something, okay, so it means that we are trying to emphasize, put our emphasis on the direct connections. We don't want information, or we don't want the transmissions to come to our say for example our substation. So what we do, we will try to diminish the value of delta. And when it is like in average case, if it is between somewhere 0.4, 0.5, 6, something like this, it basically means that the information is going to get decayed as the distance metric increases. Okay. So let's take this example delta. If we have taken it to be 0.5, then how much impact, how much importance that we are giving to the indirect neighbors that are there in 2 hop distance. Okay. What we are giving? We are giving just square it, you get 0.25. Okay. It has got diminished. And for those who are at the distance of 3 hops, even more far, we are giving it 0.125. So likewise, it is all upon your experimentation that you want to put the values, and you can get a different output every time you set the values of delta differently. And its formula will be Ci delta. It's the summation of obviously all the shortest paths, number of shortest paths that are there, but this time we are raising it to the power delta. Okay. So this is the unnormalized version. So if we again normalize it, what we do, we take the normalization parameter to be n-1 delta, because this is the lowest possible decay that is there. Okay. So this is decay centrality. Then betweenness centrality. Betweenness centrality is the measure of the centrality, the type of centrality in terms of that how good a node is acting as a crossing point between different roots. There can be so many roots in the network, taken any two nodes, any pair of nodes at a time. Then if we are taking any root, then what is the possibility that some particular node k is coming in the path of the node I and j, acting as source, as destination. Okay. So it designates a node to be central if it lies in maximum number of shortest paths. Okay. So if mathematically we want to state it, it can be stated by this formula. Again, this is the unnormalized ones. We will come across the normalized also. So here LHIJ, this is a new symbol that we are getting. Lij is simple. It denotes the total shortest paths existent between I and j. Remember, not all the total of all the shortest paths. It is only the total of shortest paths that is between a particular pair. Okay. And LH is what? It is the number of shortest paths that are existing between I and j, provided that they contain the node H. Okay. So how many such roots will be there? There can be say 10 roots between two particular nodes, and out of those 10 nodes, maybe in 2 or 3 roots our particular node H is lying. Okay. So this way we will try to find out. We'll also check out some examples, but before that let's visit the normalized version of the Betweenness centrality. This is a normalized version. Here we can see that we have normalized by n minus 1 2. This is a combination that is n minus 1 C2, that is what we write in mathematical terms. This is any number of nodes taken 2 at a time. So it's a combination, nothing else. So if we just simplify it, we get it n minus 1 n minus 2 divided by 2. So this is our normalized version. We put it back in the equation. And one very interesting fact to note is that the border nodes in any graph will have Betweenness 0. So you don't need to go on calculating the border nodes, because whenever two nodes in the entire network they want to communicate, they will never go to the border nodes to route their message via a longer route. They won't like prefer. Okay, so always the shortest route is taken. Border routes will always be avoided. So border nodes will always have a Betweenness centrality 0. Okay. Is a direct interpretation. And now let's come across the examples. The first example is our same old graph, and we want to find out the Betweenness of node 3, 5 and 15. You can just put the formula and you can find out the values, check it out. These values are 0.1, 0.2 and 0.5. Clearly node 15 is having a high Betweenness. Okay, if we try to compare it with another centrality, say degree centrality, we can see that here node 15 is a very important sharing a very important position in the network, because its degree centrality is also high. It's relatively high. When we are saying relatively high, it means that it is comparatively higher than the other nodes in the network. Obviously, it's not sharing the highest. There might be some other nodes, may not be in this network, but if we have another, say, bigger graph with denser links, then and we are taking a subset of nodes, then always we say this word relatively. One node is relatively more important than the other, like that. Okay. So here node 15, if we want to interpret, we can say that if the given graph is a logistic network, then if someone wishes to have a contract in that particular network, wants to enter into that network, wants to get some important contracts out of it, then it would be very difficult without having visited this node, this person or this department 15 as an intermediary, right. So this is how we get the interpretations out of centrality measures applied on a graph. Okay. And you can also see that here 3 and 5, they have same degree centrality, that is they have the same neighborhood size, but when it comes to acting as agent, node 5 is acting as a better agent than node 3, relatively better. Okay. Some more examples. See, here we have a star network. 6 is the center of the star, and we can see that here, if we take up any pair of node and we want to find out the shortest path, all the shortest paths are involving the node 6. It means that it's getting an absolute importance in terms of betweenness, and the normalization factor here comes to be 10, and the betweenness centrality will be 10 by 10, because it's absolutely getting visited by all the shortest paths in the network, and so we get the absolute value as 1. If we are adding extra edge in 4 and 3, between 4 and 3, then what happens? Now if we are taking as node I and j 3 and 4, and we want to find out the shortest paths, now it is not 3, 6 and then 6, 4. Now we have a direct connectivity. So now the impact of 6 vanishes by 1. So now instead of 10, we are getting over here 9. The normalization factor will remain the same, and between a centrality we can say that it has got dropped to 0.9. Another example, yet one more. Say we want to find out the betweenness centrality of 2, as we just took an interpretation that the border nodes will always have a betweenness centrality of 0. Let us see that whether it is actually true or not. So we can see that whenever we are taking any pair of node, to visit those pair of nodes, the shortest paths that are taken into account, they don't take 2 as its intermediate node, right? Which is why for every pair we are getting the value 0, and 0 upon the normalization factor will be 0. So it's an established fact now that the border nodes will always have betweenness centrality 0. Okay, now this is a linear network in which all the nodes we have just calculated the values. You can check it out. So we can see that whenever we are coming from the border area towards the core area, be it a linear graph, even if it is a linear graph, we can see that the centrality increases, the betweenness centrality increases, because as the name goes, we are coming in between, more and more towards the core of the graph. That's why C is having here 0.667, that is maximum, relatively maximum with respect to other nodes in the network. In example 6, summary of all the centrality measures that we have studied so far is given, so that you can just find out and check whether your which nodes are more important in terms of degree, or which are more important in terms of closeness. Whether there are some nodes that are important in every respect, then they share certain importance in that particular network. Now let's come to directed betweenness centrality. This is the simple directed version. So what is different here apart from the directivity, the arrows of the links? One more thing is our the normalization factor is also going to change, right? Before, what happened, we were taking n-1, n-2 by 2. Means that we are taking half of the number of total number of links, right? But now we need the twice as many as ordered pairs as there, because as compared to the unordered pairs, because unordered pairs are what they are same. A to B means B to B, B to A. So why to take 2? That's why we have taken divided by 2, right? So we have taken so that only one edge comes from every pair. But in this case, since owing to the directivity part, A to B will be different and B to A will be considered different. So we have just put twice to that value, and we have got a different formula over here. So you can just check out the directivity betweenness centrality example. Okay, here you can see that for node 2, it comes out to be 0.3, And here again, what we are doing here, say for example, we are trying to find out the betweenness of node 2. Okay. So what we will do, we will check out for every pair leaving out the node 2. So you cannot see any column for 2 over here. So 1, 3, 1, 4, but not 1, 2 we are taking, because it is a node 2 for which we are intending to find out the betweenness centrality. So 1, 2, 3, how many shortest paths are in total there, and whether those shortest paths are having node 2 in it or not. So what is the count of that? So these ratios are all on that basis given. Right. So if you calculate it, will come out to a value 0.3, which states the betweenness centrality in this particular directed graph. Now information centrality. Information often travels through the shortest paths. This is the main idea behind this centrality measure. So the network efficiency will be calculated in form of this the first one here. EIJ is the efficiency parameter, that is again the system defined one, and if you want, you can change it according to your network model. As for example, we have taken EIJ as inverse of the shortest path. Of course, it can be changed and you can get a different information centrality according to the graph or the type of application you are being you might be applying to. This is a particular version where EIJ, the efficiency parameter, is taken the inverse of the length of the shortest path. And say for example, if we have this network, a very simple network we have taken, graph G. Okay, and we want to find out the information centrality of this graph, then what we are getting for G, that is marked with the red outline, we find it that with all the vertices in that graph, the information centrality of, mind it, it's not of the node, but it's of the total network, the entire network. Okay, this is the centrality, the first centrality that we are studying of the entire network. And the value that we are getting is 0.36. Okay, and now what we can do is if we want to see the impact of removing a node from the network and then try to capture the coverage drop. Okay, so what we do, we apply a very simple formula, the relative difference here we have taken, and removing node 3. So before removing it, what we do, we have captured the value of the entire graph, and then the graph without node 3. You can see that there is another column over here, and then we have calculated IC with the information centrality with I equal to 3, and we found out 0.216. Definitely there is a drop, and if we want to calculate what is the relative percentage drop in the network, we can see that by removing node 3, which was a very important node of course in this network, which caused a drop in the information centrality by 40.90%. So this is a good interpretation. So this was all about centrality, and we'll also study even more on this topic in the next lecture. Thank you.
With this note, thank you ma'am, thank you so very much for the precious session. Dear friends, you can give your feedback for this particular lecture at info.cc@nic.in. We would be meeting again very soon. Till then, take care. Goodbye. Thank you ma'am, thank you so very much.